Thank you, Peter, for that introduction, and thank you all for coming out. It's quite overwhelming to see how many people want to come and hear the story. I should say that I wouldn't be here today if it wasn't for Peter Nine, not because he's my father. Other similarities between me and Luke Skywalker and Peter and Luke Skywalker's father aside. But because 11 years ago I was at a conference and Peter pulled me aside at a poster session and he said, come with me. He sat down on the floor, which I don't think an English gentleman should be doing. But he opened his laptop. He said, I think you should apply for this fellowship and try and come to Imperial. So at the time, I was thinking, Apple laptop? Who uses Apple? But that's what happened. So almost exactly 10 years ago, it'll be 10 years ago this weekend, I arrived here. And it's been a wonderful experience and just wonderful colleagues, wonderful physicists as well as just wonderful people. But in coming here, I came from Bell Labs, as you heard, and I took a 75% pay cut to come back to academia. And the reason we're here today is to celebrate the fact that recently that pay cut's been reduced to only 25%. All right. So what is this lecture about? This lecture is about a kind of simple question. It says, when we zoom in and in on something, and the young people here think zooming in and in is like doing this, okay? But we have other ways of zooming in. What do we find and what's really going on? What do we see? And I imagine that most of you have some kind of story that you've been told about things like atoms, and atoms are made up of protons and electrons and things like that. Okay. But it's a nice story on the surface that when you try and probe down and say, oh, those are the things, that story begins to fall apart. It's a bit like the stories that politicians or your pension scheme providers tell you. It begins to sort of break apart a bit. And so tonight what I want to do is I want to explain to you sort of how it falls apart and why it's important. Okay, why it's important to try and work that story out. Okay. So I'm going to start by telling you the story of a particle that you may well not have heard of before. Okay. The particle's called a muon, and it's it's not one of those constituents of an atom. And in fact, muons are coming barreling through this room right now. There's muons that are sort of piercing through you right now at high speed and high energy. But why should you believe me? Because you know that I tell lots of stories. So what we're going to do tonight, and it's an incredibly tricky thing, is we're going to try and show you muons. And so I'm going to bring in Pete Shadbolt, who's a postdoc with me. And we are going to try and show you muons. Okay? And it's a tricky thing to do. Okay? I might have to hold the door open. And we have built a muon detector because here's the thing. When someone tells you that something exists, until you experience it in some sense, why do you believe it? You're just believing some other person. Okay. Now, for me, when someone tells me, oh, this thing exists, and then I start wondering, well, what does really exist? I've just told you that these muons, and I'm going to tell you a bit more about muons, exist. I start thinking like, oh, well, what does existence mean? And so the way to get to the bottom of questions like that is to turn to alcohol. So that's what I'm going to do while we wait for this experiment. So actually, this is a prototype, one of the early prototypes of this experiment. The experiment really involves alcohol in a pint glass. Okay. We tried many different alcohols, gin, whiskey, vodka, and we thought better try a better whiskey. And maybe this is why it's such a tricky experiment to get going. But let me tell you a bit more about the muons that are coming through. So the muons are actually produced by cosmic rays, which are incredibly high energy particles, and mainly protons, that come, we're not even sure where they all originate from, but they hit the upper atmosphere, and some of them collide with particles in the upper atmosphere and produce these muons, so they're called secondary muons. And they're coming through at almost the speed of light, and they come barreling through. They're quite massive for a fundamental particle. They're charged, and they can easily get through the walls and the ceilings. Well, if you read Wikipedia, they say easily. But when you're sitting there trying to make it come through a detector, you begin to worry, maybe we've got a muon shield here. But apparently they've detected them 700 meters underground. Okay, so these things can just sort of go straight through. They basically see the matter around us as just sort of fairly penetrable. And what we're going to set up here is essentially a fog of alcohol. And I'm going to have to turn the lights off for us to be able to see this. Okay. And once we begin to get it going, I'm going to do that. Should I turn it off? Yeah. So, okay, so I need this. Send to both projectors. Okay. So we've got a camera hooked up. This experiment we're going to set up, it says no HDMI signal. Yeah? This experiment we're going to set up at the drinks reception afterwards, so you'll be able to actually come in and see with the naked eye. You'll be able to come and see it. I can tell you a bit more while we try and get it going, a little bit more on how it works. So you turn these lights off, maybe the TV lights, so we don't have a signal coming through. So what we've done in this pint glass is we've put some alcohol-soaked cotton wool just right in the very top of the pint glass. Okay. And what that's doing is it's sort of slowly evaporating off, and it's sort of falling down and coming down and hitting a metal plate. So this pint glass is sitting on top of a metal plate, and underneath that metal plate, we've put dry ice, so it's extremely cold underneath. And so you get this kind of snow of alcohol coming down. But we can get a kind of unstable situation if we mess around and get things right. We can get a kind of unstable situation right near the bottom of the glass. And a muon can come in, and occasionally it will hit some of the air molecules in that glass. Okay? Most of the time just goes through. But it'll occasionally hit some of the air molecules. And when it does that, it kind of knocks the electrons off them. And what that can do is create a seed. Okay? And what do I mean by a seed? Well, the clouds in the upper atmosphere, they actually form around seeds of dust. So the water needs something to kind of condense onto. And a similar kind of thing happens in here. So we get trails of like vapor trails from the muons. Okay? We get a trail that's like a cloud, a kind of streak that goes through. Okay? Now, the trick with the experiment, of course, is that we've got to get the balance right. Okay? But you can sort of think of it like a contrail from a jet aeroplane. Now, we're sitting here trying to do this thing in a pint glass. The guy who invented this experiment got a Nobel Prize for it. Okay? And in fact, several people won Nobel Prizes just from doing exactly this, looking at these things and finding new fundamental particles from the trails of the muons going through the glass. Okay. So the way I think of it is, if I'd have been the first person to do this, I could have won myself 3 or 4 Nobel Prizes, and then I would have been able to afford a flat next door to Imperial College. But unfortunately, that's not the case. Okay. How are we doing, Pete? Getting there? A couple more minutes, okay. Too many ice crystals. It's going to be all right? Okay. So, well, I'm all right. Yesterday we spent, I don't know, maybe maybe 6 hours before we started seeing them. Then we sort of got up with this formula where we managed to see them, I would say, way more than half the time. But I did actually, because I don't trust Pete, I took a video of it so that I will be able to show you a video of it, so you will get to see muons. Okay? And in fact, I'll need to show you at some level. Like even when you start seeing them, unless we see some really big ones quite strong, it takes a little bit of messing around until you really get to see them. Okay. Anyway, I'm going to keep going, and we'll hopefully see some of these trails soon. But I want to sort of step back and say, let's say we see one of these trails. I'll either show you a video or we're going to see one. Okay. Should you believe the story I told you about muons? Okay. I've given you a plausible story. I've said to you, this is where they came from, blah, blah, blah. But what you're actually seeing here is this streak of alcohol vapor made from very tiny bits of alcohol, but they're extremely tiny and yet still very large compared to muons. Right? So have I really shown them to you directly? No. But I can't show them to you directly. And the reason I can't show them to you directly is that you and I, and in particular you, are monkeys. And the only things that we can experience directly are things that we amplify up to the scale of monkeys. Okay? So essentially, what we're interested, what we evolved to be interested in the world and to experience the world is all stuff at the scale of bananas. Okay? But the banana scale is what's important to us. Okay? And so the thing about a banana is that when I say banana, you had something in mind. Okay? You had something in mind a little bit like this. Okay? It's just an object, which if I ask you to describe a banana, you'll describe it by its physical properties. And its physical properties are the things that you kind of relate to as a monkey. Okay? So you look at it, you're like, it's yellow, it's curved, and so on. Right? It has, a banana is in some sense the sum total of its physical properties. One of the physical properties that the banana is, that this banana has is that it's located here with me at the front, which sucks for you, but I've got the banana. Okay. So the sort of some of the physical properties of the banana, and some of the some of them we think of as intrinsic to the banana, some of them we think of as kind of related to the other physical properties of the other things around. Okay. Now, essentially, what we are as monkeys is what I'm going to call realists. Okay. So what is a realist? A realist is not someone who, not in the conventional sense of the word. By a realist, I mean someone who believes that these things exist, that they are there, and they have physical properties. Okay? So that scientific realism is about the existence of stuff in nature. And so you have to believe it's there, and the sort of fundamental thing that stuff has is a set of physical properties. Okay. Now, the sort of last tenet of realism is that the stuff exists, it has physical properties, but that things happen for a reason. Okay? So within a sort of a realistic view of the world, in the sense that I'm going to use realistic, I mean that stuff happens because of causes and effects. So we use what I want to call causal language to describe what's going on in the world around us. Okay? So realism, there's these sort of three tenets of realism, which are stuff exists, and it has physical properties, and sort of what science, in fact, is about is really just about understanding the causes of things. Okay? And so we do this within this realistic view of the world. And so I use language like that when I talk to you about muons. Okay? I talked about them coming in and bouncing off things and so on. Okay. That sound is vaguely worried. I'm going to flick the lights on at the back. Just tell me when to turn them off. That's fine. Okay. Okay. So we have these. We have the sort of tenets of realism, the sort of existence of stuff, and so on. And we have this sort of cause and effect.
That was one.
Fine. Lights off.
I'm sorry.
Let's turn the lights off. Okay, there we go. Now, none of you saw that, and I didn't see it, so Pete might just be trying to keep his job.
This is much better this time around.
It's very pretty.
Yeah, it's quite relaxing, but when you spend hours and hours looking at
I
it.
think in a minute or two,
In a minute or so, yeah.
it's going to go.
Okay.
It's gonna go.
You have to really create these sort of unstable conditions. I saw a tiny one there, actually. But there was one. You see that? We will set it up so you can see these with your naked eye, but actually it's easier with the camera. But at the reception, we'll bring some dry ice and try and do it. Let's wait a minute or so. Don't fall asleep. It's quite mesmerizing. There was one. Did you see that? We need a big one, like right through the middle. Now remember, there's a few hundred of them passing through you right now, kind of every second or two. But they need to collide with the stuff in just the right way so that we can actually see them. And I missed that one. Yeah, there was a tiny one there. Oh, there was one on the left. You see that? It's so cool. So let me tell you something. If you're an experimentalist, you would never try and do a demo like this. I'm a theorist. So if this doesn't work, nobody thinks I'm a failed theorist. But if I was an experimentalist, I would be much more stressed than I actually am. Okay. So there's normally this window in which you'll see a few, and then the temperatures will change, and then we won't see them. So I think, oh, there was one. Okay. Has everyone seen one? Yeah? Okay. So we'll keep going. I'm going to leave it up on the side projector there. But I'm going to go back to this one. Okay, and I'm going to turn these lights back on. Okay. So this we've seen, this is a photo I took already. Here's contrails from an aeroplane, kind of similar thing. Here are the three tenets of realism. Okay. Things exist, they have physical properties, they have causes and effects. Now, it just, some of it's just kind of obvious. You would say, why would I bother spelling all of that out? Okay. In fact, as monkeys, we've evolved to kind of add some assumptions to the realistic description of the world. Okay. So in particular, as monkeys, we believe certain things like, if I leave this banana on the bench here, it's not going to magically tunnel through, disappear on this side, end up on the other side, whatever you want to call it. It's not going to be that at some point it suddenly disappears from here and ends up under the bench. Okay? Bananas don't do that. It's just a natural thing. Bananas don't do that. Also, if I leave the banana here and I sort of go away, I do something else, I come back and the banana's not there, my natural assumption is that one of you lot stole it. Okay? That's a natural assumption. Another thing that's kind of a natural assumption for monkeys is that if I shake a branch in my tree and that shakes a branch in some other tree, okay, or some other part of the tree, that cause and effect, it's the sort of thing which should get weaker as the branches get further apart. Okay. And whatever I'm doing here that's causing the branch to shake somewhere else, that that influence is carried by something, and that in principle I could kind of block it if I really wanted to. Okay? So those are some natural assumptions about the world, and I'm going to call those assumptions monkey realism. Okay? Monkey realism is that things also behave sensibly. Okay. So monkey realism is, I think, just something which we have ingrained, and it's almost silly for me to spell it out to you. Okay? But the reason I spell it out is that when we do experiments with quantum systems, things behave extremely differently. So if instead of a banana, I take a quantum particle and I put it here, some of the time, it will just disappear from this side of the benchtop and it will appear underneath. Okay? Some of the time, I can leave a quantum particle here and I go away, and then when I look again later, it's gone, it's moved somewhere else, and it did it without there being some kind of thing that touched it and picked it up and moved it. Okay? Really strangely, although it's sort of difficult to explain why it's so strange at some level, is that if I shake a quantum branch over here, in certain circumstances, a branch in a tree that is arbitrarily far away from this tree can start shaking, and that shaking doesn't, the strength of it doesn't depend on the distance between the two branches. Okay? And I can't shield it. It's just no matter what I do, I can take the other one and take it onto a different planet and dig underground and try and shield it, and I can't. Okay? So those are things that are just experiments we do, and we see that they happen like that. And we don't, have a unique story for them. So quantum realism is just the issue that we can do a whole bunch of experiments that we find incompatible with monkey realism. Okay? They just don't obey the logic, okay, of monkey realism. But we still want to store it. We still want to know why when I put that particle does it sometimes go somewhere else? Why when I shake that branch does something else happen there? Not just why, but how. Like that, we feel like the tenets of realism, that things have causes and effects and they have physical properties, these are just what science is. Okay? So if there should be some kind of explanation for them. Okay? Now, it turns out that there are explanations, but unfortunately there are many of them. When I say many, it's not hundreds, it's sort of on the order of 10. Okay? And they are wildly incompatible with each other. Okay? So it's not impossible to come up with some realistic story for those quantum experiments, but the stories you come up with are very, very different. Okay? And so after sort of nearly 100 years of discussions like this, basically this is where physicists are at. Okay? We all have our own stories, okay? And we all like them. So what I want to do is I want to give you an example of how different these stories can be for kind of the same phenomenon. So let's take this very simple story, which is I take a particle here, I make the room very cold. Unfortunately, I'm going to have to remove all of the air, so you lot better be able to hold your breath. Okay, I make it very cold, I evacuate the room, and I take some particle, some kind of atom, and I leave it for some amount of time. And then I turn the lights back on, and I see that it's no longer where I left it, it's somewhere over there on that side of the room. And then I do the whole thing again. I do it, and then I might find it somewhere else in the room. Okay. Now, it's a quantum phenomenon that this happens, okay? That you do this experiment and you find the particle one place or another, okay? And what one natural explanation that sort of looks at the mathematical structure of quantum mechanics and says is the following. This explanation says, when you left that particle, while you weren't looking, the particle disembodied itself. It became kind of spread out. So you were thinking of it as, this sort of little lump over here, and it was when you left it like that. But it spread out and actually kind of filled up all the corners of the room. Okay. And then what happened was that when you went to look and find the particle, okay, you turned the lights on or something, then all that disembodied spread outness collapsed, is the word we use, down to a single point, the point you found the particle. Okay. That's one of the stories for that experiment. And we have a nice, precise way of describing that disembodied spread outness. So that's, that's a realistic story. But it's important to realize how strange that story is. So that story is not a very natural story from, from a physicist's perspective. And to show you why, I've got a little toy here. How good's the focus here? This is Piggy. Okay. And Piggy has the property that he also can become disembodied and spread out. Okay, here's Piggy. And then Piggy will sometimes just come back and congeal back to be just in one spot. Okay? So Piggy, it seems, is a good analogy for the quantum particle. Okay? But why is Piggy different? Piggy's fundamentally very different. The reason is that when he or she when Piggy comes back together, it takes time. And the reason it takes time is that Piggy's kind of elastic, and one bit at the edge has to kind of pull on another bit and slowly bring all this stuff, bring him back to the way he was. Okay? And Piggy is also, something that's quite different between Piggy and the case of the quantum particle is that you can imagine that when Piggy is spread out, I do something where I measure like Piggy's ear in one position and his tail in another. Okay? So you can hope that if you did a good enough experiment, you could see a little bit of Piggy over here and a little bit over there. But the quantum case is completely different. That if you take the story that the quantum particle also forms kind of a disembodied, spread out thing, then you never find a little bit of the particle over here and a little bit over there. Okay? And you never find that it's taken some amount of time for the particle to sort of collapse back to this point. So if that is your quantum realistic story of that process, it seems like a very kind of extreme event, okay, from the perspective of what might be natural physics. Okay. But there are people that they are the monkeys on one side of that, fine, and they believe things like that. Okay. Let me now give you a completely different story that people try to give about the exact same experiment. So in this story, they say, no, the particle doesn't disembody. What happens is that your knowledge disembodies, your knowledge spreads out, your information about the world is what disembodies, but the particle doesn't. Okay. Now, what does it mean for knowledge or information to spread out? Okay. To help with that, I've got another little friend here. This is, now be quiet, this is a Norwegian blue with lovely plumage, but it's asleep. Okay. And I have this little parrot here. Okay. And I'm going to have to ask you all to close your eyes. Okay. At the moment, you know that the parrot's here, in front of the room. But you close your eyes, and then I'm going to wake the parrot up. Okay. And now it wants to fly away. Some of you are not closing your eyes. Okay. And now the parrot's flown away. Okay. Now, where is the parrot? Unless you're a cheetah. Okay. The parrot, from your perspective, could be anywhere in this room. So your state of knowledge of the parrot is spread out. It could have been in this corner, it could be at the back, could be anywhere. Okay? But you still believe that the parrot itself is somewhere, okay? That it's stuck there in one point. Okay, so when someone, if I then say, oh, where is the parrot? So who has the parrot? Someone ended up with the parrot. Where is the parrot? Okay, there's the parrot in the fifth row. As soon as you see the parrot, okay, you know instantaneously that that is where the parrot is. Okay? And it doesn't seem strange to you that your information about the location of the parrot collapsed instantaneously down to, oh, the parrot's with the sort of ugly bald guy in the middle. That's not a strange thing. So it's not strange for your information to change instantly. You kind of have the spread out information, you don't know where it is, you get some more data, and then it changes instantaneously to, oh, it's over there. Okay. Now for me, when I think about that quantum experiment, remember we do the experiment, we see what happens. Now we're just trying to find the story about what happens. So when I see that particular experiment, to me it's very compelling that what actually spread out was some sort of knowledge or information about the world and was not the actual system. Okay? And, but of course there's people on both sides of that divide. But, and it's not that I'm naive in the sense that I know that there are many strange experiments quantum mechanically, this just would seem to be less strange, that type of explanation. Okay? And so for a large part of my career, I thought a lot about looking for that type of explanation of the world. And then about 5 or 6 years ago, one of my students, Nicholas Harrigan, who actually is the person who invented this type of muon detector. And he's actually giving a talk over in the Science Museum right now, which is much better than this one. They're giving out like ice cream made from nitrogen. Anyway, so Nick, during his PhD, he kind of opened up a little bit of a crack in that story. Okay? Basically, the sort of upshot of his work was that you can't attribute all of the spreading outness to just a lack of knowledge of where the particle is. Some of the time, some amount of it, small amount of it, kind of has to be real in some sense. Okay? Now, it was disconcerting, but it's one of those things, because it was a fairly small effect and so on, I sort of felt like, well, there's got to be some sort of loophole in this, and a lot of this is mathematical proofs, and you think, well, maybe we messed something up. But then a few years later, a different student, Matt Pusey, he took that crack and just leveraged it open and caused the dam to burst. Because the upshot of Matt's work was that you can't think of any of that spread outness as just a spread out of lack of knowledge of something, as just information. It has to be, if you take some very plausible assumptions of the world, which are really just the assumptions of realism, then if you just accept the assumptions of realism, not a monkey realism, but just fundamental realism, which to me are sort of almost incontrovertible assumptions, then you have to accept that this spread outness is real, okay? This kind of disembodiment. And that goes against everything that kind of makes sense to me about how the world should operate. So my way of dealing with that has been this. All right. No, so my way of dealing with it has been that, but on weekends, and I think a lot of crazy thoughts. Okay? I think that there must be something fundamentally wrong in almost how we formulated the questions that we're asking. So I am going to get to, some crazy ideas from that. But first I want to give you a motivation for why these sorts of questions, these seem like, very philosophical and abstract questions, why they're actually of practical importance. So the starting point is that as monkeys, we're good at thinking. Okay? We like to reason about the world. That's part of, we want to find better bananas. We want to find other monkeys to do monkey business with and so on. Okay. So we have our way of thinking about the world, and we make those assumptions of monkey realism, that the world behaves in this kind of normal way. And in fact, we've managed to go far enough that we can build a device which thinks like us. Okay? And I mean, of course, something like this, a computer. Okay? And it's a remarkable thing that the following is true, that we can build a computer out of stuff that obeys the laws of monkey realism. Okay? So when you look in a computer, you might see things and they look like, very small and complicated. But when I look inside, I see bananas. Right? We can make a computer out of stuff that obeys the laws of monkey realism, and that in doing so, we can make this computer think with the same logic as us, and it can do all of the same logic as us. Okay. It's a very, very deep property of the world that was first realized by Alan Turing. Okay. He was actually thinking not about, making PowerPoint slides, but he was actually thinking about how people think. But the flip side is that computer can only do the same thing. It's built out of monkey realistic principles, and what makes it so deep is that computer can only do the same kind of logical thinking as us. It can do it, but it can only do the same that we can. Okay. So this is a problem if what you want to do is take quantum experiments and systems and the laws of quantum mechanics, and you want to try and understand them using the regular computer, because although it's faster and so on, it's kind of constrained by the same principles that our brains are constrained by. Okay. So it's quite difficult. And people have won Nobel Prizes for just finding better ways of trying to approximately simulate some kind of quantum system. Okay? But we now know from these sort of theorems that we can prove about the fundamental differences between any quantum realism and monkey realism, that those are doomed to fail, that there never will be a way of simulating that kind of quantum stuff, of knowing what's going on in our quantum experiments using a computer like this. Okay? So I think that that's a deep insight into the world, that it's a little bit of a negative insight. But the flip side is the following. The flip side is that what we want to do then is, instead what we're going to do is to build a quantum computer. We're going to build a computer that the elements of which, and this is a picture from a lab downstairs, okay, the elements of this quantum computer will fundamentally be quantum. They will be obeying all of those kind of strange things that quantum systems do. Okay? And if we can build such a thing, and it's a very tricky experiment to do it, but if we can build such a thing, we know that we will be able to use it to sort of understand quantum experiments better. That computer, we might not understand it, and the regular computer might not, but that computer will be able to understand it. So, for example, the sort of thing that can be useful for is you want to design some new kind of drug, pharmaceutical industry. Okay? If you want to design some new kind of drug, well, you don't want to just be randomly putting stuff together. So if we can build the quantum computer, because the quantum computer, designing a drug is about understanding chemistry. Understanding chemistry is about understanding the fundamental interactions between a whole bunch of quantum particles. So the quantum computer will be able to kind of look at it and go, oh yeah, I know how that works, and design the drug for us. Okay? They will be incredibly powerful devices for us. Because I think it's important to sort of plug why these foundational questions are interesting. The flip side is that we struggle to find the reasons or why the quantum computer is better than the normal computer. It's difficult to find problems. Some of them are obvious, like drug design. Some of them are not so obvious. And the only insights we have today on the difference in power come from understanding the difference between quantum realism and monkey realism. Like, why are all the quantum realistic stories quantitatively different from the monkey realistic stories? And we have ways of quantifying that difference, and that's given us some insights into this problem. It's going to be interesting once we have these devices, how exactly we deal with working out what to do with them. It's almost like we'll ask the one device to help us program the other one. It's a lot of strange things that go on. Okay, so that's my plug for why I should be employed somewhere like Imperial, where we do good, hard, practical science, and not sent off to a loony bin like Oxford or something. The philosophy department, I mean. We don't have a philosophy department here. Okay, so maybe you're some young, enthusiastic student, you're like, well, I don't care about the practical implementations. I really want to understand better what's going on in quantum theory. Okay. And so what I would say to you is don't tell the funding agencies. Okay? You can tell the Leverhulme Trust. In all the years I've been looking for support to work on things like this, the Leverhulme Trust are the only people that have given it to me. Okay. All right, so now what I'm going to do is I'm going to go on to talk about crazy stuff, okay? And I'm partly doing it, and this is just one, you have, when you get to this, when you feel like you're trapped in this corner where everything about trying to understand quantum mechanics just looks so strange, you just start looking for crazy and crazy things. But the reason why I want to outline, like this is literally a crazy idea I've been playing around with for 6 months or something. And I want to do it because I think it's so half-formed, but I want students to see that it's okay to be crazy. We educate you not to stop you from having ideas. We educate you so you can filter out the bad ideas. Okay? That you can do that on your own. So at some level, like normally someone would get up and they would be like, oh, here's some research I've done in the past. I'm going to just tell you like the nuttiest thing. I was like, what's the craziest thing? This is the nuttiest thing, and it's sort of part of research right now. Okay, so to summarize so what I want to do is okay. Let me tell you the vague idea. The vague idea is that space and time are like the taste of a banana. The taste of a banana is something which it's useful for monkeys. We have evolved to find bananas taste well and good and so on. It might be part of the physical properties of the world that we think are important. But I don't think anyone would argue that the taste of a banana is really a fundamental physical property, okay? That it would still be relevant to other types of animals or on other planets and so on. Okay? So I want to sort of explore the idea that space and time are human-centric. We use the word anthropocentric. That they're physical properties that we've evolved that at least are useful for us. But probably for whatever's going on at that microscopic scale, they're not relevant. And you'll notice a lot of those examples I gave as to strange things. Quantum branch here can shake one arbitrarily far away. And this thing can disappear from here and end up there. A lot of those strange things are somehow couched in space-time. Not all of them, but a lot of them. Okay, so what I'm going to do is I'm going to give you an example. Okay, so let me first say the following, because this is a lesson all physicists know well, but might not be obvious to everyone. That when you remove the importance of humans from your physical story, sometimes it's incredibly powerful. There's a classic example of that, which is called epicycles. Epicycles were the trajectories that it was assumed that the planets took around the Earth when we thought that the Earth was at the center of the universe. Okay? So we thought we were so important. Okay? Here we are. We're like, hey, yeah, we're at the center. Okay. And we saw that the sun went around the Earth. So, the sun revolved around us and the fixed stars revolved around us. And then we noticed that actually some of the planets, when you watch them, most of the time they go around one direction. Sometimes they turn around and go back, then they come forward again and so on. And so as our measurements got more accurate, we had to say, yeah, everything's going around the Earth, but a lot of them are following a very weird kind of spirally trajectory like this. And actually, so this is from about 400 years ago, 500 years ago, this figure. And it's written on it in Latin, so I can't even read which planets are which. But the trajectories are quite strange. It's not like there's this one spirally one, but they come out and then come back and so on. It's a very, I guess, pretty in some sense, but it's a very complicated explanation of the exact same system, which is this. When I take the sun is at the center of the universe. Okay? The exact same physical system is described now in a much simpler way. The sun is at the center of the universe, and the planets just go around it on circles. Okay? That was the simpler explanation. And so my hope is that one day when we remove the taste of bananas, when we remove space-time from our story, that things will suddenly look a lot simpler. Okay? The problem is, I don't know. Like, it's so hardwired into me. I just don't know how to do physics and without kind of having some concept of space-time. It's very difficult. You sit there, and by the time you're on your third or fourth beer, I just can't. Okay. But I'm going to give you one example, at least, of how it can be fundamentally different. Okay. So I'm going to tell you first a quantum experiment that we could do, okay? And in this experiment, I would release a particle from the end of the bench. And the previous one, I let it kind of go anywhere in the room, but this one I'm going to constrain it such that it can only run along the edge of the bench, and if I wait long enough, it'll end up on that end of the bench. Okay? But now what I do is at a particular time, a fixed time that I'm going to call 1. The units don't matter. Okay, 1 second, 1 minute, 1 hour, doesn't matter. At a fixed time, I look to see where the particle is. And I can arrange this experiment so that when I go and look, it's a sort of standard quantum weirdness, I will only find the particle either here, or over here, or over here, but I will never find it at any of the in-between locations. And in versions of these experiments, we can do things where, the particle ends up there and you never see it in an in-between location. You're like, well, did it actually cross in between? How could it have gotten from there to there without crossing in between? And so on. Okay. But in this version of the experiment, we're going to do the very simplest version, which is I just look once. I look at 1 second after, or 1 minute or whatever, and I see that the particle is in one of these 3 locations and never anywhere else. Now, it seems like a standard, that's just quantum weirdness story, right? Every physicist in here knows, I could work out a way of doing that experiment. Okay. So, if you went to the explanation for this experiment in terms of the disembodied kind of spread outness of a particle, which now, seems to me like that's forced upon us by realism. This is the sort of upshot of this kind of work, that seems to be the only option. That explanation would look something like, well, the particle spreads out along the bench, and it does so in a kind of wavy way, and it waves around, and the waves kind of build up in this location, and they build up in this location, and in that one, and they interfere against each other somehow in between, and then I only ever see the particle when I go to look. That wave goes vroomp down, collapses down instantaneously, and bang, I find the particle here, or I find it there, or there. It's kind of random. Every time I do it somewhere different. But the key point is I don't see it anywhere in between. Okay? So that would be the quantum realistic explanation of what was just an experiment we did. Okay? And it seems like, well, we're going to be forced into that type of explanation. But to try and convince you that maybe there's other types of explanations out there, I'm going to tell you a parable. This parable is set in Malawi only because I grew up in Malawi, and it's a beautiful country. I think you should go there, and this is my kind of tourist brochure for Lake Malawi. Okay. So I thought I could throw that in. And so the story is going to involve a young Malawian boy. Here he is. Okay. And his job is every day, every morning, he goes at the same time of day to meet the fishermen when they come in. Okay. And he picks up some fish, and he runs them to his father's grocery store. Okay. So here's his father's grocery store. It's called Let Them Talk Grocery. In Africa, they often like to use funny names for places and things and so on. But Let Them Talk is even a bit out there for that. But it probably makes sense because nearby, sort of a few shops away, is the people always complain hardware and estate agents. And it's hardware and estate agents. And it says, we sell bolts. I love it. Okay. So the little boy's job is to pick the fish up and to run, which are at the lake, and run them up into the village, into to his father's grocery store. So here he is. He runs along this path. Okay. Now, living near the path is an old man. Okay. And this old man wakes up every morning, and he checks his clock, and he sees that he wakes up at the same time of day. Okay. So he goes to the window, and he looks out, and he looks along this path, and he sees the boy. Okay. And yet, when he looks, he only ever sees the boy in one of 3 locations. Okay. So because I'm no good at animating stuff on computer, I'm actually going to use someone who looks like a little African boy to just come and help me illustrate what's actually going on. So this is David Jennings. David used to be a postdoc in my group. He's now a Royal Society Fellow, setting up his own group, and he's actually one of the best physicists I've ever met. Technically and in terms of intuition, and today I'm going to make him do something completely silly and trivial. Okay. So here is the story. Okay. Maybe, can you walk along the front? I don't know, maybe it's easier. Then you can see. Okay. So the story is that, so here, when the old man wakes up, he always looks at the time 1. Okay. He looks at the time 1, and he sort of looks out and he sees the boy. And he finds the boy in one of those 3 locations. Okay. So, so go back to the start. So now, what can can you walk along there? Okay. So some of the time when he's woken up, he wakes up. We deliberately didn't practice this because I wanted to see him. He wakes up and the boy is in the first location. Okay, and the clock really has just gone from 0 to 1. His clock. But you'll notice that this is an African clock. It doesn't have another hand. Many things in Africa are broken. So some of the time, something completely different has happened. So go back to the start. Some of the time, what happens is the clock actually goes around a cycle before it comes back to the number 1. And so now the boy has moved all the way here. Okay. You should be in location 2, I think. I think 2 is the banana. Right? Okay. So now the old man still sees the same time on the clock. Okay. He looks down, he sees the boy, and the boy is over here in location 2. Okay. Some of the time, we go back and we do it again. We go through the same thing, but now we've gone through 2 revolutions of the clock before the old man looks and sees the number 1. Hey, he is smart. Okay. So you can see that the old man, his impression is, I'm making a measurement at the same time. Okay. And depending on the number of revolutions that the clock has taken beforehand, it can affect where he sees the boy. Okay. I think, is that clear enough? Yes? All right. So I think you can sit down now. Okay, so what that tells us is that a situation in which we are like the old man, right? The time that we're measuring, a situation where that time is not in a kind of one-to-one correspondence or some natural order of events with the microscopic time of the particle, then weird things can look like they happen. Okay? So here's the old man, the boy in the 3 locations. I would like to say that, it's just a parable. I have to finish the story. So the old man, he started thinking, it looks like this boy is like disembodying along the path every day. Okay? It's like, that's really weird. And it looks like he's like oscillating around and doing these strange things. Okay? When of course he's not. Okay? But this being Africa, and it's a sad fact that they label people as witches because they really believe in witches. And then they just chop them to pieces. And that's what happened. So David, to act out the rest of the story. Yeah. Okay, now the physicists in the audience, I know, are sitting there going, it's a nice story. Yeah. But where's something concrete? Okay, and I only have one slide of mathematics in this whole talk. I was sort of warned off it, and with good reason, I think. But so this is just an aside for the physicists. You might say, it's just a story, and it probably is. And what I'm trying to say is that there can be some interesting things maybe happen if we take on viewpoints like this. So here's just a technical aside for the physics nerds. Okay? We're quite used to the following fact about physics, which is if I have the probability density for a particle, and in particular, the only thing I know how to apply this kind of thinking to at the moment is the harmonic oscillator, that I might find, there's high probability the particle's here and 0 that it's there and high probability it's there and so on. So we have a probability density of the position of the particle for a given time t, and that time is the time that we measure. And we know that that probability cannot be computed by assuming that there exists a standard normal probability distribution over the position and the momentum of the particle, a Liouville distribution. Okay? That you cannot compute that by marginalizing out the momentum of the particle really having a position and a momentum for a given time t. That's not possible. Okay? If you try and do it, you end up with negative values. Negative probabilities don't make sense. So we just this is it's sort of a proof in some sense. The way people would say it is that you can't sort of simultaneously have a position and a momentum of a particle. Okay? But if you take the viewpoint that, there's really 2 times. There's a macro time that I'll call big T, and then what we're really measuring here is the position of x given big T. And there's some little micro time, little t. Then it turns out, and this might just be mathematical coincidence, I don't know, but there does exist a joint probability distribution over a position, a momentum, and a microscopic time, little t, okay, given the macroscopic time t that you make the measurement at, such that when you marginalize out your ignorance of little t and p, that you recover this. Okay? Don't know, could be coincidence, might not, It's sort of a weird thing because it's a probability measure. We're in one of these annoying types of things that has to be equivalent to distribution theory on a Hilbert space, and so you can't switch these integrals, otherwise we would have this. That's the only technical content, more just so that my colleagues don't kick me out of this place. All right. So I'm going to finish. I've got 2 slides left. This slide is a painting by Geraldine Cox, and it captures for me why I think it's important that we come up with some realistic story for what's going on in quantum theory. The reason is that somehow quantum theory was relevant before we even evolved, before this universe existed. And this painting captures that. In this painting, it's a painting of 2 physicists looking at a photographic plate that is the spectrum from a star. And a spectrum from a star has sharp lines in it. It's the color of light emitted from a star ends up having sharp gaps in it. Okay? And if you look at this painting, what's beautiful, it's a bit hard to see here, is that all the human features of the painting are indistinct, but the spectral lines are very sharp and they almost float off the painting. And the spectral lines are the things that quantum theory lets you calculate. It lets you calculate exactly these distances. And it just seems to me that means something in quantum theory is independent of us, the humans involved in the whole theory, and so that we should be looking for some kind of story about what's going on. And although the stories we have now are really crazy, some people believe in parallel universes. Some people believe literally that realism fails at the microscopic level, that actually we can't talk about things having properties and causing the outcomes of experiments, that somewhere in between the bananas and the particles, something fundamentally changes. And I don't even know how I would do science if I believed that. But, there are people that try to come to terms with that kind of thinking. So I think it's an important quest. I don't really have anything like an answer that I would like to give, despite the advertising for this talk somehow trying to indicate differently. It's traditional at the end of a talk like this to say something like, well, I would like to thank my group who did all the hard work, but no, they didn't. But I would like to thank them because they are what make coming to work every day worthwhile. When you get drowned under admin and teaching and all of that kind of stuff, the enthusiasm of your own troop is awesome. And so here they are, ranging from my first PhD student, Hugo, Nick, who you've heard a little bit about today, there's Matt. These first two rows, these guys are all graduated. These are some of the current students. These are the postdocs, Gary, Pete, Dara, and David, who you've met. Pete, who set this up for us. Okay, and I'll leave it at that. Thank you.